So you have met Lasso, which selects features by zeroing the weak ones, and Ridge, which stabilizes correlated predictors by shrinking them gently. Here is the annoying part. Lasso alone stumbles on groups of correlated features, arbitrarily keeping one and tossing the rest, while Ridge alone never simplifies anything at all. So which do you pick, sparsity or stability? What if you did not have to choose? ElasticNet says, take both penalties, blend them, and get selection and stability together. It has quietly become the default regularizer for wide, messy data. Let us break it down. So why blend two penalties instead of committing to just one? Here is the trade side by side. Commit to Lasso alone and you get sparsity and feature selection, but it behaves badly with clusters of correlated features, arbitrarily keeping one and dropping the rest, and it caps how many features it can pick when predictors outnumber samples. Commit to Ridge alone and you get stability across those correlated features, but it never zeroes a single coefficient. Either way, you are giving something up. ElasticNet refuses that dilemma. It adds both penalties at once, so the L1 part still produces sparsity and picks features, while the L2 part keeps correlated features behaving as a group and restores stability. You get selection and robustness from a single model, which is exactly why it thrives on wide, correlated data. So how does the blend actually work? Watch the recipe come together one ingredient at a time. Start by adding the L1 penalty, the Lasso ingredient. This is the part that pushes weak coefficients to zero and performs the feature selection, giving you a sparse model that keeps only what genuinely matters. On its own, it would be plain Lasso, sharp at selection but fragile whenever features start to correlate. Then add the L2 penalty, the Ridge ingredient. This part handles correlation. It encourages groups of correlated features to be kept or dropped together, the grouping effect, and it restores the numerical stability Lasso lacks on its own. Suddenly, the model stops picking one feature at random from a cluster and starts treating the whole cluster sensibly. Now tune the mix between them. A blending parameter, often called the L1 ratio, decides how much of each penalty you want, sliding smoothly from pure Ridge at one end to pure Lasso at the other. This is your second knob. Finally, minimize the combined loss, the squared error plus that blended penalty altogether. The overall strength and the mix are both chosen by cross-validation, and out comes a model that selects features and stays stable at the very same time. Strip it back and three ideas define ElasticNet. It is a weighted blend of the L1 and L2 penalties. Rather than choosing between Lasso and Ridge, ElasticNet adds both to the squared error loss and lets a mixing parameter decide the balance. It selects and stabilizes correlated feature groups. The L1 part still zeroes weak coefficients for sparsity, while the L2 part pulls correlated features in together, so related inputs survive or drop as a group instead of being picked at random. It carries two knobs, both tuned by cross-validation, the overall penalty strength and the L1 to L2 mix. That extra tuning is its only real cost, and like every penalized linear model, it needs its features scaled first so the penalty treats each coefficient fairly. Alright, let us lock in the essentials. ElasticNet is a regularized regression that combines the L1 penalty of Lasso and the L2 penalty of Ridge inside a single model, getting the best of both at once. The L1 part gives you sparsity and feature selection, while the L2 part handles correlated features as groups and restores stability. It carries two hyperparameters, the overall strength and the L1 to L2 mix, both tuned by cross-validation to fit your particular data. That makes it the default regularizer for wide, correlated data like genomics, text, and marketing, where features are many and clustered. If you like machine learning served without the jargon, come and explore the rest of the collection over at standarity.com. See you there.